You know that nearly 8 out of 10 people will experience back pain at some point in their lives. And the major indicator of this is bad posture. And this problem has only gotten worse as we spend more and more time at our desks. So that's why Marco, Gerard, and I created PostureBuddy, which is a system that classifies seated posture using RFID tag localization and video inferred user skeletons.
So now, before going into the exact details of how our system works, we want to just give you an idea of what each of these components look like. So at the top, you can see two different types of RFID tags that we happen to use. The one on the left is circularly polarized, while the one on the right is linearly polarized.
Our system design is split into three main modules: the data module, the processing module, and the score prediction module. First, from the data module, we collect readings from the camera from a user sitting down and RFID readings from the back of someone, and we pass that into the processing layer. The processing layer does some extraction to infer your skeleton, and among some other things to extract the rest of the features. Then we pass those into our score prediction module, where we generated a computer vision score and an RFID score based on models that we created using labeled data of us sitting down, looking forward at the camera, moving to the side, moving out of the picture to get a representative data sample so that we could build a model based on those features. Then we combine those scores by averaging them and outputting a binary classification score with 0.5 as the threshold, so anything above is classified as good posture and anything below is classified as bad posture. Next, for setting up the RFID tags, we had a couple of challenges. First challenge was with phase ambiguity. Since our reader only goes from 0 to 180, we wanted to unwrap these phases using this numpy function to unwrap. The second issue that we ran into was with noise in our measurements. As you can see in this scatter plot, we have a lot of different noisy measurements mapped to the same distance, so it's a little bit ambiguous. But you can also see that when averaging out these values, we can get a more consistent data reading and have a better mapping from our decided distance. So we created a running average of the previous 20 measurements, and this seemed to smooth out a lot of the noise.
Another important pre-processing step was converting the phase reading into distance. We found that distance is phase times the maximum distance over 180 degrees, where Dmax is quite small, just around 8.67 centimeters. When we tested this, it turned out to be a quite precise measurement of distance. We placed the RFID tag in position A, which ran a distance of roughly 3.5 centimeters. If we then moved the RFID by 2 centimeters in the direction of the reader, the distance value calculated increased to around 5.5 centimeters.
Yes. And in order to implement the prediction scores for the different modules, one of the packages we used specifically for the computer vision component was OpenPose. And it essentially takes an image sample from the laptop webcam, and it produces images of skeletons of the user, as seen in the pictures below. Now, the approach we ended up going with was taking the skeleton and extracting some features from it. So that includes the shoulder length, the neck vector, which is the relation of the base of the chest, the tip of the nose, shoulder neck angles, as well as ear-to-ear horizontal alignment to detect head tilting. We fed into a neural net to get that binarized posture score. We found it was about 89% accurate in classifying unknown postures with these features. It was also a lightweight model with very few layers, and it ran quickly, and it performs even better when calibrated to a specific user, which is something we integrated into our real-time application. For the sake of thoroughness, we also investigated training a CNN on just the skeletons generated by OpenPose, where we found that because this took more layers and had a large risk of overfitting to the specific training images of the skeletons, it was far less accurate and it was much slower. So we ended up sticking with the first approach. Finally, the model used for RFID utilizes a similar idea. We average over 20 samples to reduce the noise, as Marco mentioned, and we feed that into a neural net to get a posture score. And we found that averaging the readings over the 20 samples greatly reduced the noise and improved the accuracy of the model, but it also reduced the responsiveness of the model to changing postures in real time.
Here you can see the system just returned its first score. For context, Marco is currently wearing 3 RFIDs on his sweater. Marco will now move in different positions relative to the camera, and the scores will be measured for each one. Finally, in the end, when Marco is done working for the day, he goes away, and soon the combined CV and RFID model will return none. These are the 2 plots which were automatically generated after the demo. Over most time steps, the 2 models agreed, but in a few, they predicted a different binary value. This is important because it means we can leverage CV in certain situations and RFID model in others. trying to combine both in order to be as accurate as often as possible. In specific, this TV model has a big challenge. It is not good at detecting anything that is out of sight of the laptop camera. Your posture might look fine to the camera, but only because it cannot see that your upper or lower spine is curved. As you can see, these are two pictures of the same exact moment. From the front, the CV model, even we, mistakenly thought Howard had a good posture. In fact, Howard had a bad posture, which is very clear if you look at his spine, which is sadly curved. This is a scenario that is really difficult for a CV to classify, but instead might be easy for the RFID tags on Howard's back.
When evaluating our system, we wanted to encompass the full range of motions that a user could be in while our system is turned on. So that includes sitting forward and looking at the computer screen, moving to the side, moving out of the frame, getting up and going out of the room. So we ran our system for about 20 minutes, collecting 20 different individual posture readings, and we have our results below. As you can see, the computer vision and RFID scores seem to be pretty accurate, but the combined scores seem to provide the highest accuracy. It's worth noting that the two samples that the combined scores made incorrect were actually edge cases where both the RFID and the computer vision components were very confident but in conflicting directions. We believe that future work could go into combining these scores in a more sophisticated way such that those incorrect readings fall in a correct bucket instead.
Another approach, which we tried but did not end up using, was inverse aperture. With this approach, we were able to find a value for the spatial angle, which is the angle between the normal to the motion and the line connecting the tag to the reader. Assuming that the posture movements moved each RFID reading by roughly 5 centimeters, we were able to construct the following equation for A. Then, we found the spatial angle by finding the value of theta that maximized the value of A. Unfortunately though, this spatial angle was quite noisy, and so we decided not to incorporate it into our model.